Vasudev Shyam from the Center for Creative Fundamental Research and Creative Education in Bangalore. I'll talk about geometric quantization and shape dynamics.
Firstly, I'd like to thank the organizers of this conference and this parallel session in particular for allowing me this opportunity, particularly because I had to change the abstract for this talk and to do it. So I shall get on with this then. So as we've heard from Dr. Gomez in the morning and from Dr. Kozlowski and even from Mateo to some extent, shape dynamics is a theory that is equivalent to GR in some respect, but what we have here is the absence of a Hamiltonian constraint, and instead we have these two first-class constraints, which are those that generate diffeomorphisms and conformal transformations. So, yeah. So classically, the extended Hamiltonian that I'm considering looks like this, where that is the true Hamiltonian, which generates dynamics, which generates evolution with respect to the York time, and these are the diffeomorphism and the conformal morphism constraints, respectively. Now, this conformal factor solves the Lishnerovich-York equation, and there's a construction which I won't go into, but basically there's a deparametrization constraint which leads to this Hamiltonian. So the physical Hamiltonian is given by this, as I mentioned. Now, because of this, what we can try doing is we can look at the problem of finding the inner product as completely separated out from the problem of dynamics, because we don't have to worry about imposing invariance under the Hamiltonian constraint. So dynamics and kinematics are separated. So I thought the best way to go about doing that is to consider the BRST construction, where we get rid of having to have invariance under the constraint separately. Instead, we just consider a BRST charge, and we have a differential with respect to that, and the zeroth cohomology with respect to this differential will be the ring of observables in the classical phase space. So since it's a first-class system, the BRST charge is quite directly constructed, like in Yang-Mills theories, and we have, so this is an abelian constraint, so the only other terms that pop up with so these are the ghosts and the ghost momenta, and the only other terms that pop up with the ghost momenta in this part are the ones which have to do with the commutation between two diffeomorphism constraints and the diffeomorphism and the conformal morphism constraint. And the BRST differential is given by this, where this is the Hamiltonian vector field corresponding to the BRST charge, and this is the extended symplectic form, where the phase space is going to be both the metric and the momentric sort of variables, and this fermionic, anti-commuting ghosts and their momenta. So I'll also get into that in some time. So now this by construction is nilpotent, because it's a first-class theory, and at least classically it's going to be nilpotent. And as I said before, the observables are going to belong to the zeroth cohomology class. Now, if I shall move to the non-minimal sector of the BRST, so that, I'll tell you why it's relevant later on, but so doing that is also direct. We just need the two Lagrange multipliers and their momenta, and we extend the phase space by augmenting it with this. And corresponding to that, we have the anti-ghosts and their momenta. And as we know, the momenta corresponding to the Lagrange multipliers aren't really there in the action. So we have two first-class constraints being we have two of these first-class-like constraints which are linear in both of these momenta, and they contribute this non-minimal They have this non-minimal contribution to the BRST charge. Now, yeah, so all we need to do now is choose a gauge fixing fermion of this form, where I've chosen this Faddeev-Popov-like gauge for these two, Faddeev-Popov-like gauge fixing, basically derivative for these two functions here. And the extended Hamiltonian, which is usually sum of three parts, is just these two because it's gauge invariant under both the conformal morphisms and the diffeomorphism. So we're not going to have the other term popping up here. We're just going to have this, and we're going to have the BRST differential of the gauge fixing fermion. Now I shall move on to the crux of the talk, being the BRST extended geometric quantization. So all quantization efforts that we've had so far when it comes to the metric representation of quantum gravity were done a long time ago in the context of Wheeler-DeWitt quantization. And there the major problem was that imposing both, as I said, imposing both Hamiltonian invariance under the quantized Hamiltonian constraint and the diffeomorphism constraint proved awfully problematic, and there was basically no control over the space of states, and it was basically a very formal construction. Now, I'm not saying that this is going to be exact. I mean, it's still going to be a little formal, but we can go a bit further. So now I'm going to try and show you what shape dynamics buys us in this respect. I'm going to try my best to do so. So the geometric quantization procedure that I show here basically follows through in the following steps, being first we choose a polarization of the phase space, and we quotient out the phase space by said polarization. Then we choose, then basically quantization or pre-quantization surmounts to finding a holomorphic line bundle over this polarized phase space, where the curvature of this line bundle will be proportional to I times the symplectic form. And the polarization I choose is going to be the vertical polarization. I'll put real in bracket because that only applies to the this bosonic phase space and perhaps not this anti-commuting one. And you have to note that the analog of the symplectic form here is not going to give us Poisson brackets. Instead, it's going to give us this anti-commuting bracket when we actually take the form. So they're both going to be spanned by their functional derivatives with respect to the momenta. So in essence, quotienting this out from the phase space is going to be something like moving to the configuration space. So basically, we don't need the other. So even if we do the pre-quantization, we still have too many degrees of freedom. We need to cut out half of them. So that's what we're going to do next. And of course, quantization implies that we need to complete this space with an inner product. And that's what I'll be talking about. So, okay, so the space of extended geometric quantum states, okay, so this is the pre-quantization condition that I was telling you about. And in essence, there are going to be sections of this line bundle, which is given by this. And these sections so happen to correspond to the ones at gross number plus or minus m by 2 for m bosonic constraints. This is going to be plus or minus 2 because we have 4 bosonic constraints, 4 times infinity, but we've chosen an appropriate gross number operator. So we they admit an expansion in powers of the ghosts. And now this size 0, and all of them depend on, they're all of the metric. They're all functions of the wave functions of the metric, and possibly the York time. Since I'm not considering dynamics, I haven't put that in. So this is what they look like. Now the action of the metric is by multiplication, and the momenta is by functional differentiation, and similarly with the ghosts and their momenta. And if you notice, this is like a Clifford algebra with 4 generators. 4 generators. So the ghost number operator, which I choose, is going to be given by this. Now that's why. Okay, so corresponding to this ghost number operator, this state. So this big I is a multi-index where it's each one of these little ones, so every one of these indices is included in that. So the highest I, so this is like the highest of the powers that we've chosen before. So the very first one is going to have ghost number minus 2, and this one's going to have ghost number plus 2. And now, of course, those are not the physical states. The physical states have to correspond to the ghost number 0 singlets. Now, the ghost number 0 singlets they have to be attained through. Well, basically they'll belong to this, but there's this really interesting isomorphism between that and this, where this is the non-minimal contribution only, and this is just the minimal BRC charge. Now I'll show you how this works in terms of the particular wave functions later, where it's more enlightening. So just given this, the inner product of these states is given by this formula. Now, this inner product is not square integrable in general, and of course, I'm not going to go forward and use it, so it's not the physical inner product yet, or it's not what I purport to be. Now, but it's useful to note nevertheless. So, the quantized BRST charge ought to be nilpotent, but now I have to be really careful. So this was mentioned by Enrique Gomez in the talk this morning. Now I don't expect there to be anomalies, given that the constraint quantization in the Dirac sense is also anomaly free, because the space of states that I actually get here are the very same as what we get by trying to naively Dirac quantize the BRST extended phase space. But obviously that's going to give us non-null doublets. So if you want the null singlets, what we need to do is take the non-minimal contribution. So that's why I've done that. Now, so it's something along the lines of, okay, I've written Q. So Q squared psi goes to 0 is basically equivalent in this context to having the proper representation of the constrained algebra and the quantum Hilbert space. Now I'm just putting a caveat in here because this conclusion has been, I've come to this conclusion due to a private communication I've had, and none of these results have been published as of yet. So let's assume that. Now I'll skip forward to the main message. So the hope is to tentatively resolve the inner product problem to as much as we can, given that we have these very new properties. Now what we can't do is, what I'm not going to claim I'm going to do is give you an explicit form of the eigenfunctions of the metric and the momentum acting on the wave function. So I'm going to leave that as an indefinite scalar product, namely saying that it satisfies all the properties except for non-degeneracy and positivity. And so if this admits a decomposition of this form in terms of some basis, then this would look like this. So I don't even know if this is going to be true. So I'm not going to comment about that because there are several ways to do it, but they're all very formal, and I don't want to do anything awfully formal, any more formal than I already have. But what I can do is, given some inner product between two metric states, I can tell you how to make it gauge invariant, or BRST invariant in this case. And basically, that is to find gross number 0 states, and that's very simple. We take the eigenfunction, the 0 eigenfunction with respect to all of these operators, and that isomorphism formula I showed you before, that's what it looks like in terms of a wave function. So we're going to have a tensor product between these two, and this is what each one of the operators acting on it will look like. So obviously it's the 0. It's the 0 eigenvalue with respect to eigenvalue with respect to each one of these operators, and it's always going to be BRST closed, and it's going to be BRST exact only at gross number plus or minus 2. And yeah, that's part and parcel of the construction. Now, but if I just took the scalar product between two of these states, then I'm still going to run into an indeterminate form of which looks like this. So if I just took psi and psi of this form, it's going to be something like this: delta of 0 times this indefinite scalar product that I chose of as a function of the metric. So the regularization that I show here is what gets rid of this. So I'm not making any claims about this as of now. So that's what I'm going to present henceforth. And so yeah, that's the construction of the physical inner product. Now, I'm sorry, went too far. Okay, so up to exact states, we can use the BRST pairing of these two cohomology classes and find a basis expansion for this state, alternatively, instead of the tensor product that I showed before, in this form. So in general, we're going to have something like times a bunch of that times psi alpha. So for the gross number 0 states, we're not going to see any of those gross terms cropping up. So the regularized inner product is so the regularization is going to be of this form. So this is how we go about regularizing it, and explicitly it looks like this, and this regularizes this up to this indefinite scalar product that I've chosen. So, and what this buys us is, at least up to that, we can find the projected kernel of physical observables, quantized physical observables, and they look like this. And basically, this previous slide is like saying, so this essentially is something like the projected kernel of the identity operator. And so in general, for any observable, which is of course BRST invariant, the projected kernel will be given by this. So now, the conclusion is, due to the simple nature of the first-class constraints and true Hamiltonian generating evolution with respect to the York time, the problem of quantum kinematics and dynamics are separated in the sense that we don't have to worry about the inner product being invariant under the Hamiltonian constraint. And up to this indefinite scalar product, we can feasibly construct a regularized physical inner product. Now, of course, in the future, we definitely have to make something of this, because this wouldn't even work if this were to be 0, and that would be very problematic, or if that were to be infinite. And also, the dynamics is a big problem, because as Dr. Gomez mentioned, and even Dr. Kozlowski mentioned, the true Hamiltonian is a non-local function of the phase space variables, and in this representation, it seems almost impossible to quantize it in general now. Yeah, so these are some references, apart from the shape dynamics ones that I've used. So thank you all for listening.
Questions? What's the advantage of combining geometric quantization with BRST quantization?
Well, it's not the advantage. I mean, well, there's no advantage. It's just that there are several ways to, in the end, construct gross number 0 states. But I've chosen to use geometric quantization because it makes some sense to actually talk about things like the metric acting by multiplication and the momenta acting by the momenta acting as functional derivatives, because actually what we're doing in geometric quantization is so consider a flow of something like the metric or some phase space functional. Then I write it as f of q and p. Now, in essence, we're doing something of this sort. So the operator will look like this. Now, if you put the momenta in, you'll get the functional derivative. If you put the metric in, you will essentially get the multiplication, which respects the polarization. So it makes a little more sense to talk about this rather than just transformation theory of Dirac. So that's why I chose that. But apart from that, there's no real insightful reason that I can give you.
So you're doing geometric quantization first, and then...
Well, not really. So it's like trying to hit two birds with one stone. It's do geometric quantization of the BRST, non-minimal BRST extended phase space, all in all. And luckily what that gives us is the very same BRST state. It's the, as I said, it's the states which would be equivalent to what we get from Dirac quantization. So yeah, there'd be the ghost number that I mentioned.
Any questions?
No, so can you go back a couple of slides? Just so the problem with so you say finite physical product is given as, and then you say that there is a problem with this because it might still be indefinite.
Oh no, not that it would be indefinite. If this is like 0 something for the eigenfunctions we've chosen, then that's just 0. I mean, there's nothing really happening there. Or if it's like infinite or something like that. So I mean, as you know, in the past, the attempts to construct the inner product is always something like Klein-Gordon, where you have surface element, and you have these states where there's like this, you have this formally written out, it looks like this, and you're trying to impose diffeomorphism invariance in some sense. All of this it's all very formal. I mean, you can't even make sense of it. So that is the problem, and it's also a problem in functional analysis because no one knows of a rigorous functional measure, of a functional integration measure on Riem, as in on the space of metrics. So yeah, I mean, this sort of stuff is not really well defined. So that's not something that we have to worry about because that is as of now. So shape dynamics doesn't tell us anything about that. That's just functional analysis, I feel. So that's why. So.
Thank you.
If there are no other questions, I will thank Vasudev again.